Consider this baseball field that I've drawn here. There are three regions to this baseball field. We have the fair territory, home run territory, and of course the foul territory. The fair territory is going to be everything on the inside of this quarter circle. The home run territory is everything beyond the home run line. And then the foul territory is everything um, that's kind of past these two lines. This is a very simplified system here. Now we just have these two lines at a 90-degree angle in this quarter circle here. There's two variables that we need to define any kind of hit that a batter gets in baseball. There's the angle, and we're going to define the angle from being this bottom foul line here. The angle that they're hit, so say a baseball is hit to this spot right here. We have the angle, and this is our angle alpha, and D is the distance that it's hit. So it's this is hit to right there, so that's the distance from. And I'm saying that the home base plate is right there in the corner. It's not quite, but in the simplified system, that's where we're going to say it. Now, using these two variables, we can define each of these territories. So the fair territory is going to be every angle the ball is hit between 0 and 90. It can't be on 0 because that's on the foul line, and it can't be on 90 because it's also going to be on the foul line. Now, the distance is, we're going to say it can't be 0 and it cannot be, and we're going to say the distance is about 400 feet. That's on average where it's at, the home run line. It's going to be 400 feet. So the angle is between degrees and the distance is between feet. Now that's the fair territory. Home run territory, let's actually make this less than or equal to 400 feet. Home run territory is going to be the same angle, can't be a foul ball, and it's going to be everything greater than 400 feet. That's when you get a home run. And finally, everything else is in foul territory. I can write it like this. I can write 90 less than or equal to angle, less than or equal to 360 degrees. 360 degrees ends up being a full circle. It goes all the way back around, and it's on the foul line. So this is actually equal to 0 degrees. And so I don't have to worry about this nothing equals 0 because 360 does equal 0. And then we're going to say it can be any distance greater than or equal to 0. That's going to include right there on the spot if the ball didn't move at all. We're going to say that is a foul ball because it's on here on this vertex. Okay, so as you can see here, we've used inequalities to set up these regions for a baseball field. And that's typically what inequalities do. They set up constraints for some kind of a system. And what you get is solutions that are within certain constraints. So like if we were looking for a home run territory, we're going to get this set of solutions, all the values in this blue region here, in this fair territory region. It's going to be sometimes going to be an interval that you're going to look at, or it's going to be some kind of region on a graph, things like that. That's what you'd expect from a system of inequalities. Now, we have to discuss an important topic of inequalities before we can really look at them and use them. First off, we must let's look at this thing where negative 100 is less than negative 1. That's just a true statement. And then from this, we're going to add 10. So adding 10 onto this is going to give us negative 90 is less than 9. That's true. Once again, we're going to go from this spot here down to here, and we're going to subtract 10 from both sides. It's going to be negative 110 less than negative 11. That's still true. From this original statement, multiplied by 10, we're going to get negative 1000 is less than negative 10. True. From this original statement, we're going to multiply by negative 10. That's going to give us 1000 is less than 10. This is false. However, we can make this true quite simply by just flipping the inequality. And this will be true. Okay. The next one, we're going to divide by 10. So we have negative 100 divided by 10 is negative 10. A negative 1 divided by 10 is negative 1/10. That's a true statement. And finally, we're going to divide by negative 10. That's going to give us positive 10 less than positive 1/10. This is a false statement. Once again, we can make it true by just flipping the inequality. This is a true statement. And this is the key thing to note whenever you're working with inequalities. When multiplying or dividing by a negative, you need to flip the inequality. If you don't do that, you're going to actually invalidate your whole process and you're going to get a wrong solution. So make sure to keep that in mind whenever working with inequalities. Now, actually working with inequalities, when you're working with them and trying to solve them, you can solve them just like you can with equations. So just think of this inequality now as an equal sign. This is a linear equation with one variable. We can solve it by getting the variable by itself, except we're going to consider the inequality there. We're just going to leave it there and just kind of treat it like an equation sign. But remember, if you multiply or divide by a negative, flip it. Okay, I'm going to first distribute the 5 because I don't want the parentheses. We had 15 minus 5x less than or equal to 3x minus 1. Let's get the x's together. I'm going to subtract 3x to this side, and then in the same process, I can subtract 15x, or sorry, just 15 to the other side. That'll get the x's together. We negative 8x less than or equal to negative 16. And here I can divide by negative 8. I'm dividing by a negative, so we need to flip the inequality. And I get x greater than or equal to 2. Now, in addition to this solution, which we have a solution here, we can also graph this solution. X greater than 2, well, 2 is this. X is greater than or equal to it. If it's equal to, that means it can be this border point. And it's greater than it, so it's going to be everything on this side of the real number line. So I'm going to use a bracket and draw a line. And that tells me that it is the interval 2 to infinity. And these are the 3 different ways you might be asked to write an answer for an inequality. You have this actual inequality symbol here, x greater than or equal to 2. You have the graphed notation or the graphed thing on the real number line. And then you have interval notation. Interval notation being probably one of the more important ways you write this, but just keep that in mind. There's these 3 different ways to answer these. Okay, this one has fractions. We can treat fractions just like we did in linear equations. We can multiply everything by the least common denominator. In this case, 10, 15, and 6 can all go into 30. So I'm going to multiply everything by 30. That's going to give me, distributing the 30 into here, 30 and 10 reduced to 3, so we're going to get 3x minus 8. 30 and 15 reduced, we're going to get 2, 10 minus x. And the 30 and 6 reduced to get me 5. So we're going to get 5x minus 1. Let's distribute. 3x minus 24 minus 20 minus or plus 2x. 5x minus 5. All right. We can combine like terms. We have 30x and 2x, negative 24 and negative 20. So we're going to get 5x minus 44 greater than 5x minus 5. Subtract the 5x from the left. And you see they both cancel, and we get negative 44 is greater than negative 5. And this, of course, is a false statement. So there's no solution. So just like in the linear equations, you can get false statements or true statements to get no solution or infinite solutions. So again, we can kind of have, conditional inequalities that you can solve. We can have, inconsistent or contradictory inequalities and that kind of stuff. Give it a try in number 1. Now, sometimes we have inequalities that look like this. They've got 2 different sides, and these are called compound inequalities. Really, this is the same thing as 2 inequalities. We have negative 6 is less than or equal to negative x over 2 minus 4, and negative x over 2 minus 4 is less than negative 3. But we can combine them because we have the same negative x over 2 minus 4 in both inequalities. We can combine them into one statement, and it's actually easier to do so. But you can't just split it up like this, and you solve these just like we did already. We're going to solve by getting x by itself. So plus 4, then we get negative x over 2, negative 2. We're going to multiply by negative 2 on both sides. And then that gives us 4 less than or equal to x. Of course, I forgot when we multiply by a negative, we need to flip the inequality. So we get this. Same exact process here. We're going to add 4 and then multiply by negative 2. And that means we need to flip the inequality. And you can see that this is actually the same thing. Once again, we have x the same, so we can actually combine this into one inequality. That means that x is bounded between negative 2 and 4. So I can draw this like this. It cannot equal 2, so I'm going to use a parenthesis, but it can equal 4. And that is a thing it graphed. And of course, the interval notation is just that. Of course, you can flip this whole inequality around. It's the same exact thing. But what's interesting, though, is that you don't actually have to split this thing up to solve it. We could just take negative 6 less than or equal to negative x over 2 minus 4. And you can see we did the exact same thing when solving this. We added 4, then we multiplied by negative 2. Well, that's essentially what we're doing here. We're just going to add 4. Whatever you do to the middle, do it to each of the sides. This becomes 1. This becomes negative 2. And we're going to multiply by negative 2. And now we're going to flip each inequality. And we're going to get 4x negative 2. And we get the exact same statement twice. So you don't have to split it up if you don't want to. If it makes more sense to split it up, then do that. Whatever is easiest for you to understand. Give it a try in number 2.